So the topic of this lecture will be probability everywhere. I am going to talk about the probability and also the how to use probability in cryptanalysis, which is a new field that we're going to explore, which actually belongs to the study of cryptography. So last time I actually showed one clip from the World Science Festival talking about the frequentist and Bayesian probability. So we actually all know that from advanced pre-calculus. So frequentist probability are mathematicians making or statistician making deduction rely on experiments. For example, if all the data from one experiment is showing a normal distribution, it's showing the trend of a normal distribution, which would actually behave like a bell curve, then the data, the median, will actually have the greatest probability to occur. And when the frequentist probability, like people who are predicting based upon the experiments, they might predict on one event from their common trends. For example, if in the experiments, the data are behaving in a normal distributed way, then they might make deduction based on the trend. And the Bayesian probability is not quite the same as frequentist probability. Bayesian probability is mostly commonly used in most fields of math and branches of math, and it is somewhat called conditional probability because all the deductions based upon the prior knowledge or the hypothesis that people are making. So I said Alan Turing preferred Bayesian probability. That is not because Alan Turing only uses Bayesian probability. Actually, a lot of his work shows some frequentist probability. But the thing is, when he is doing his major research, he is using Bayesian probability. For the most of the time, people are using Bayesian probability to predict the accuracy of some clinical tests. For example, the COVID-19 test would be one of the example. If the test result is showing false, that doesn't mean that you don't have COVID-19. There is like a probability for that to happen. And you could actually use Bayes' theorem to determine the probability for that to occur. And the notation of PAB means the probability for the case A to occur based on the prior knowledge of B event will occur. And this conditional probability are commonly used in many discrete math. Like when we're flipping a coin, we will and we're calculating the probability for getting a tail after flipping a tail. That would belong to the Bayesian probability. And there are two major kinds of randomness. So the first kind of randomness is the quantum randomness, and the second kind is the classical randomness. So for quantum physicists, they would actually prefer the quantum randomness because they kind of believe that it is a true randomness. But for like mathematicians, especially like on discrete mathematicians, they will use classical randomness because we're actually ignoring a lot of hidden variables. For the quantum randomness, it is claimed that all the possible outcomes are truly random because we don't know any further measurements. The very classical experiment would be the Schrödinger's cat. I think we all know about Schrödinger's cats, but I'm going to talk about that. So for that case, we are putting a cat in a box and we're releasing a toxic gas. We don't know the cat will live or die when we are not opening the box. Assume that we can't see anything that is going on inside of the box. And this picture actually shows the formula that could describe this experiment. The coefficient in front of those two like symbol of cats would mean the probability for things to occur. And in these two are kind of two variables in this experiment, which are two outcomes of the experiment. And the classical randomness would be like things like fair dice rolling and coin flipping. We're not considering any hidden variable because when we're rolling dice, we're not considering on how we roll the dice, but only the combination of faces of the dice and the sides of the dice. One example for that is on there. Okay, this is from Professor Potion Low's lecture, and I attended his lecture in my middle school. He talked about like a very specific way of rolling a six-sided fair dice when you're only rotating it in the way that the dice only falls on four of its sides. You're actually eliminating the probability for the dice to land on two of its sides. This will actually help you to win some sort of games or actually gain you a fair advantage over your enemies or whatever. There is one video about the fair dice problem. There are 5 main types of fair dice. If you're interested in the video, you could go to YouTube search number file and fair dice problem. And there's also like a very short paper about those 5 kinds of fair dice. I think that's very interesting because I did one of my projects, I think 2 years ago, on a 8-sided fair dice. And we were thinking about how to label each side with different numbers and which labeling would make the dice fair. Okay. So you might see in the 2 previous slides that I talked about Alan Turing preferred Bayesian probability and also classical randomness. Because when Alan Turing was working for the secret agency of UK, during the World War II, the exact same time when he invented Enigma machine to break the German code, he is actually considering using those 2 main things in his cryptanalysis. So cryptanalysis is the analysis of a language system. Maybe during Alan Turing's time, he is investigating on the English word system and also the German system in order to break the code, because a lot of trends in our language system and how we actually use our language system, it's helping for us to eliminate some of the possibilities of the experiment, of the like the different kinds of outcomes that we could possibly make based on the ciphertext. Here is a code, a very easy cipher that we could try to break. So this is our ciphertext. And given that we're only considering 26 letter, we are not considering uppercase and lowercase different. And given that the plain text was in English, so we could, how can we actually solve this and convert this to the plain text?
Well, I see the letter E by itself, so that's definitely got to be A or I. And
Yeah,
given its place, I think it would probably work better as A, maybe.
yeah, you're correct. Okay, so a way to actually decode the cipher is through uh, it's by looking at the frequency for letters to occur in like different language in our language system. So these are two texts pulled from two different literature works, and you could see the trend that the letter E occurs for the most of the time in the language system. So we might assume that the letter that occur for the most of the time would be E in plain text if we use the frequency counter to analyze the ciphertext. And for the access to the frequency counter, this is just like two screenshots from the online frequency counter, so you could basically do it yourself. When I actually put the ciphertext into the frequency counter, I see that the letter E occurs for most of the time, and the second most frequent letter is I. So I could say that the author of the ciphertext loves to use E and I in his or her writing. We know that E is quite commonly used in the text from the previous analysis. We could actually use like more, we could actually analyze more texts from different books to learn more about the language system, but we only use two texts from like two different literature works to analyze it. So we could probably guess that the letter I is E because E couldn't be E. We can't read the ciphertext, and the ciphertext is it is given that the plain text was in the English language system. That means we could actually the text will be comprehensible. But if the ciphertext E is the plain text E, then we can't read the whole thing. So that is not quite possible. So our second guess could be the ciphertext I would actually be the plain text E in the plain text. So this is our guess. So P represents a plain text letter, and we actually convert this letter to a number. We usually use the order of the letter in the alphabet as the number for P, and the C is the ciphertext letter. So one single letter in the ciphertext, and we are also using the order to denote this thing. So we know that P plus 4 is congruent to C mod 26. A mod 26 because we have 26 letters in the alphabet, and we are making a guess on a ciphertext I, it's E in the plain text. That means shifting the whole alphabet 4 places afterwards. So yeah, so let's try that. Okay. So the previous modular equation would help us to know that the plain text A would be the ciphertext E, and so on. So this isn't like the shifting of the alphabet that we are guessing. So we could try out for the for the first few words. So M would be person. So it will be I, and R will be N, so in, and X would be T, L would be H, and I would be E. That's the, so this kind of seems right. And we just shift the ciphertext on 4 places forward to get a plain text. So yeah, this is a story in the on invitation from Crypto and Math Club email. I'm gonna introduce another category of cipher. So all the stuff that we have learned about, I think that we have talked about, are all belong to one single category. The cipher that we just talked about, which is shifting cipher / substitution cipher / Caesar cipher, is a simple cipher. It is simple because we are only using one cipher alphabet to encode. We're moving all the letters for places afterwards to create a new alphabet to encode all the things that we have. We sometimes have 2 keys, but we're essentially doing the same thing. This kind of cipher is called monoalphabetic cipher. And the cipher that a new category of cipher I'm going to introduce is polyalphabetic cipher. Could someone make a guess on what it is? Anyone?
Oh, polyalphabetic cipher is that when you first follow one rule to translate the text to one text translate to another text and use this text to translate to another text, and eventually you will get your original text by decipher it. But there's 2 rules of how to decode it like that. Is that what is polyalphabetic cipher is?
Well, it's actually using 2 cipher alphabet to encode the plain text, or 2 or more actually. So you will have like different shifting things that you will use in encoding the cipher. So one example for that is a Vigenère cipher. So it is not invented by the mathematician Vigenère on the right here. It is invented by an Italian mathematician, and it is named after Vigenère because he actually analyzed the cipher in his book. And we're going to know more about the Vigenère cipher. I'm going to talk about why it is polyalphabetic, and also why it is using 2 or more cipher alphabet to encode. So if you're interested in a Python version of decryption and encryption, you could also find one on YouTube by Aladdin Person. I am going to use one example to introduce or to crack a Vigenère cipher. You could perhaps see what Vigenère cipher is doing by looking at this example. So I'm going to introduce back our 3 virtual characters, Alice, Eve, and Bob. So Alice and Eve are trying to communicate, and they're using encryption and decryption to encode their messages and to use keys to actually decrypt their messages on each of their ends. And Eve is the evil person who is listening to their conversation in a certain way. This time, Eve is very fortunate. Eve knows that the key that Alice is using and Bob is using to encrypt and decrypt their cipher is the word dog. So this is very uncommon because we usually use one number or one single letter to encode our cipher, encode our plain text. And Eve heard that the ciphertext that is communicated through Eve is BSROCC. So Eve is trying to figure out what Alice and Bob are talking about. We said the Vigenère Cipher is a polyalphabetic cipher. So could anyone actually predict how the cipher will work? And also a hint is the key, because the key is a word instead of a number. What does that mean? Anyone?
I think that this might be the one that I use, but it's like where you have the alphabet and you take the letters from the alphabet in the key and then you move them to the beginning and then you shift everything over. I'm not sure though.
Okay, this is actually harder than I expect. I expect everyone to like understand it, but not really. Okay, I'm gonna talk about that. So a valid guess would be we're using some cipher alphabets to encode the plain text, which is what BSROCC. And the keyword help us to determine the cipher alphabets. Previously, we're using, for example, one number 4 to shift the whole alphabet 4 units afterwards. So A will be corresponds to E in the plain text. And so this time we're using some cipher alphabets because the key is actually dog. So we could expect something different than that. On the key in the previous example that we talked about might be E because we're shifting the whole thing for 4 units afterwards. So we might guess there are 3 cipher alphabets that are used in this system. And those cipher alphabets are determined by the keyword dog. And maybe D will mean shifting the whole thing 3 units afterwards, and O would mean something different and things like that. So the ciphertext could be divided into 3 bits long blocks. The first block would be BSR, and the second block will be OCC. And for each, we're using the cipher, the key dog to encrypt it, to decrypt it. This encryption system is essentially 3 modular equations, or you could think of it as 6 modular equations, but this time I'm just going to use 3 to better illustrate on what polyalphabetic cipher is. This is taken from our previous lectures. So these 2 functions actually tells you what decryption and encryption are doing. So for the decryption, we're taking the cipher and we're taking the key to generate a message. And for the encryption, we're using message and the key to generate the ciphertext. Message and the plain text are the same thing. And this time is not essentially time, but also it also could mean some function that is applied on C and K or M and K. So these three are our modular equations that we're using. So P0, P1, and P2 would mean letters in the plain text, for example. And we're saying that 0, 1, 2 denotes the remainder of the order after mod that by 3. So we're taking the order of B, S, and R. So B will apparently be 2, and S, I don't know. Okay, so the key will be the same. So we have like 3 keys. We have the keyword dog. So the first key might be the order of D, and the second one would be the order of O, and the third one would be order of G. And we're applying the methods that we used to this encryption system, but we're just like what we did to the shifting cipher thing. And these 3 things will be congruent to our ciphertext letters. And because we have 26 letters in the alphabetic system, so that will mod 26. And the 26 might be different in different situations. When we're using ASCII code, the uppercase and lowercase are different. We're using different numbers to denote them. And also we also have, for example, number to represent a space and things like that. So these actually differs, but we're going to use 26 here, and we think that we just assume that the uppercase and lowercase are the same. Okay. So the ciphertext, if we are using numbers to the order, their order to denote them would be 2, 19, 18, 15, 3, and 3. So the key would be 4, 15, and 7, because D is the 4th letter and O is the 15th letter, and so on. And we're just plugging in all the stuffs into our equation and try to solve for the plain text letters. So for B and O, we use the first one to solve, and S and C, we use the second one, and R and C, we use the third one. This is because of the length of the keywords that we're using. So the plain text would be yellow. So B shifting force would be 1, 2, 3. So it would be this. It will be Y in the plain text, and we're doing the same thing to O. And for S and C, we're using like another shifting thing to do that. So this is essentially the Vigenère Cipher. I'm going to talk about the visualization of the Vigenère Cipher. So for the classical shifting cipher, Caesar cipher /Caesar cipher / substitution cipher that we talked about, the visualization are like these. So we sometimes use a circle, and for example, say the inner circle would be the cipher text, and the outer circle would be the plain text, and we have 1-to-1 correspondence for each letter in plain text and each letter in the cipher text. Or we could just use a line to represent this. And for the Vigenère cipher, cryptologists actually invented this Vigenère tableau to visualize the cipher, what's going on in the Vigenère cipher. I'm going to talk about how to use it by using the previous example. You could also think about other visualization for Vigenère cipher. I mean, that's a thing for us to think about. So we talked about the encryption and decryption system. So for each, we need to know 2 of the variables to determine what is going on. We could also only know 1 variable to determine it, but that would be much more complicated. And how to do, you could actually think about how to do it if we only know the ciphertext, not knowing the keyword. That would be much more harder to do. So for the tableau, when we're using the tableau, we need to know 2 variables to determine things. So we write our keyword here, and this is the thing that we don't know. This is supposed to be where we have our plain text. We will put all the ciphertext here. So maybe initially it will be just a line of letters, 2 lines of letters. And the intersection between the plain text and the keyword would be our ciphertext. So yeah, for B and O, we would have the intersection between D and L, and also Y and D. And for C and R, it would be the intersection of G and L and G and W. So this is a way for us to figure out the thing that is going on. And once we know what is on the keyword, and once we know what is the ciphertext, we could actually find out the intersection. And we could then determine what is the plain text by using the intersection. So this is a way to solve the Vigenère cipher by using Vigenère tableau. By knowing 2 variables, we need to know the keyword and also the ciphertext to determine what is the plain text. So these are 4 questions for us to think about. Why do we talk about Alan Turing in our informal lecture? So I am gonna include Alan Turing and his work in our future meetings. And what is the role of probability in cryptography? You could actually Google it, or you could just guess. And how secure is the Vigenère cipher? We are essentially going to think of it in regarding the probability. So that's why we're saying that the topic of this lecture is probability everywhere. And also how to decode the Vigenère cipher when we only know the ciphertext. So this is much more harder, but you could probably think of some of the techniques in the cryptanalysis. Cryptanalysis might help us to decode Vigenère cipher when only knowing the ciphertext. We might going to include this in our future meeting, but not this time. So my main references, if you're interested in probability and more stuff, you could go to World Science Festival, and the video actually takes on an hour for you to watch it if you really want to watch it. And you could go to find an introduction to mathematical cryptography. This is a book that I am using for our lectures. So if you're interested in additional information, you could also go to an introduction to math. You could also refer to this book. I think we're doing chapter 4. Yeah. So that's it for today. We could probably watch the fair dice video from Numberphile, but okay, my computer is not working. Let me try to stop share. Now let me change my screen. Go to Numberphile. The Faraday's problem is very interesting. It has to do with the group theory, but we're not going to talk about group theory. So I'm going to pause this recording.